Hello everyone and welcome to the next differentiation presentation, which is all to do with optimization. Now, a lot of students rightfully say often, well, it's all good and well learning about differentiation, but how is it going to ever help me in real life? Well, here is the opportunity to tell you all about how businesses and companies might want to use differentiation to either, for example, maximize profit, which would be very important to them, or to perhaps maximize the space inside the packaging that they're making. This would all be done through differentiation. So I'm going to show you an example because these real life examples come up a lot within the A-level maths course, and as I say, the whole idea of being able to take a real life question and solve it using differentiation techniques is called optimization. So this company makes open top boxes, and you can see that the piece of card that they use before anything is done with it is measuring 24 centimeters by 9 centimeters. And what happens is that the corners are cut out from the corners of the rectangle, and then the sides are folded up to create the box that you're seeing here. So a very simple box. And this company wants to maximize the volume that the boxes can hold. So it's very tempting to think that by taking away the smallest square possible from the corners of the original rectangle, that's going to create the maximum amount of volume inside the box. And we will find out whether that's true as we progress through the question. So here is my rectangle with my corners taken out, and we're going to make the length of the square that I'm taking out of the box equal to x. And the first question to ask is, well, what are the possible values that x can take? Well, clearly x has got to be bigger than 0, or we wouldn't be taking any square out at all. But we also have the restriction of the width and the length of the box. So the width of the box is 9. So if I half that value, because we're taking a square from both the top and the bottom, then the maximum value that x could be is 4.5. Any more than 4.5, my value of x, and it's going to be bigger than the 9 centimeters that is the original width. So my value of x has to be between 0 and 4.5, and I'm gonna rest that there for a moment, and we will need to come back to that in just a bit. So what we need to look at now is finding the formula for the volume of this particular box, because if I need to maximize that volume, then I need to have that volume formula before I can do anything with it. So, of course, the volume of a cuboid is found by multiplying the length by the width by the height. So if I've taken these squares of side x out from the four corners, what therefore will be the resulting length, width and height by doing that? So first of all, you'll see that on the diagram now I've shown quite clearly those x values that I'm taking away from the corners of the original rectangle, and that therefore will result in a width of 9 minus the 2 x's that I've taken away. There will be a length of 24 minus the 2 x's that I've taken away, and then as shown in the 3D diagram in the bottom right hand corner, that will also mean that the height of the box is of course x. And to find the volume of my box, I would now multiply those three dimensions together, and that will give me my volume. Okay, good. So now I need to maximize that volume, and we already know a little bit about maximum values and where they occur on the graph of the function. So if I'm going to have to differentiate this function, I need to expand the bracket. I can't differentiate this formula by simply differentiating each of the brackets. That doesn't work, and therefore my method is to first of all multiply out the brackets. So this is the result of multiplying out the first two brackets, and then if I multiply all three values or all three terms within the bracket by x, this is my final volume formula. So we need to find the maximum volume, so we need to find the rate of change between v and x. We need to find the gradient function so that we can then find where the maximum value is occurring on the original volume curve. So make sure that we write or use the correct notation. When we were dealing with equations of y in terms of x, then the gradient function was dy by dx. Now, because our formula is v in terms of x, then our gradient function is dv by dx. So please make sure that you use the correct notation when you are differentiating. And the answer to that is as of course how it's always been. We multiply by the whole power and reduce the power by 1. So the next job is to find, therefore, where is that maximum value occurring? Where is the maximum point on that original volume curve? So to do that, I'm going to find the stationary points on the original curve by making the gradient function equal to 0. So this was all covered in the theory of differentiation on the previous presentation. So I've replaced dv by dx with 0. And then I can use my calculator, because this is quite a tricky quadratic to factorize. I can use my calculator to find those values, and it turns out that there are two values of x that will make the gradient function equal to 0, and they are at 2 and at 9. So to decide which one is the maximum, or which one is going to give us the maximum volume, I can do various things, but one of the things I can do is to find the second derivative. So the second derivative, remember, is used to find out whether my stationary point is a maximum or a minimum. So the second derivative, I'm differentiating dv by dx, and I get 2v over dx squared will equal 24x minus 132. If I take my first value of x and place that into the second derivative, I find that I get a negative number. I get minus 84. Now I'm not really concerned about how negative that number is. I just need to decide whether I end up with a negative value or whether I end up with a positive value. And because I've ended up with a negative value, we can tell the examiner, if this was an exam, that because we have a negative second derivative, the implication is that we have a maximum point, which of course is exactly what we need. The other reason why we know that x equals 9 is not going to give us our maximum volume is because, if you remember from a couple of slides ago, we decided that x can only take values between 0 and 4.5. So x equals 9 does not fit into that interval, and therefore that is not going to be the value of x that gives us our final answer. So again, another reason why x equals 2 is the value that we need. So now we know we are going to get that maximum value, or the maximum volume, if we use that value of x equals 2. I can now place that back into my original equation to find that maximum volume. What is the maximum volume that I am going to achieve from that box? It's going to be when the squares that I cut out from the corners have length and width of 2. And if I place that value of x back into the original volume equation, I end up with an answer of 200. Any other value of x between 0 and 4.5 is not going to give me a volume that's bigger than that. That's the maximum volume that I can achieve. And I've contextualized this by also putting some units on the end of my answer, because I was told at the start of the question that the measurements were all in centimeters. Now, if I show you this diagram, which is the curve of the original cubic that represented the volume, you can see exactly what we've just worked out in diagram form. So this part of the graph is the part of the graph that we're interested in, because this is the part of the graph that represents x values between 0 and 4.5. And we know that our x values for the situation that we had couldn't be anything else other than a value of x between 0 and 4.5. So this is the only part of the graph that I'm interested in trying to solve my question. There we see the maximum value when x equals 2. We decided that this was the value of x that we needed to use to find that maximum value, and we found that using various techniques, but one of them was to prove that it was the maximum value by using the second derivative. We also decided that x equals 2 could only be the correct value because it was the only value of x between 0 and 4.5. Here is our second turning point when x is 9. It's not the value that we need, number one, because it's actually giving us the minimum value, but really there's no context to this minimum value because it's not in that selected area in the top left hand corner, which is the only part of the graph that we need to consider for when solving this question. Good, and that is optimization. There are lots of different questions that you could be asked about optimization. Like I said earlier, you might want to maximize profit, you might want to maximize volume, you might want to minimize costs. Of course, if a company wants to make the most profit, they have to minimize costs. So you might have a cost formula that you're asked to minimize. You might have to derive the formulae for yourself, or you might get given them. There's all sorts of different possibilities that can occur. So the best thing to do is to have a go at these two exercises. I'm expecting you to ask your teacher lots of questions based on what you're seeing within these two exercises, and within your homeworks that you're going to be doing for us over the next few weeks, you will see an increasing number of optimization questions on there as well. So make sure that you ask lots of questions about this topic, and I will see you on the next presentation. So thanks for listening, get plenty of practice, and I will see you next time. Thanks very much.